Okay, any questions about last class? Okay, so let's do a bit recap of what we did in the last class. What we were trying to do is to think of a system where we have, in this box over here, you can see red molecules are the gas A molecules, red B are the gas B molecules, and gas B molecules, and you have a partition in between. And the question is, when you open this partition, you know through common sense that A and B would mix together. It won't look like red on the left and blue on the right. It will mix together. And we wanted to understand what is it that makes this mixing process spontaneous. And we are doing this at constant pressure and temperature. So we know that the condition for spontaneity is that delta G should be negative at constant pressure and temperature. And that's what we showed here. For this, we derived a delta G mixing, which looks like, let me write it down in today's class. We derived that delta mixing of G is equal to RT XA ln XA plus XB ln XB. And you can see how to generalize it for a 3-component system or a 4-component system. You will just have XA ln XA, XB ln XB plus XC ln XC. Mostly we are looking at 2-component systems. For 2-component system, we normally write XA is equal to X and XB is equal to 1 minus X. So we get delta mix G is equal to RT X ln X plus 1 minus X ln 1 minus X. And this is an important expression. First of all, it shows to us that delta mix H is equal to 0 and delta mix S is equal to minus R X ln X plus 1 minus X ln 1 minus X. How did we get delta mix S? We got this by using the idea that dG is equal to VdP minus SdT, our integrated first and second law of thermodynamics. Therefore, S is equal to minus partial G by partial T at constant P. That's what we use to get delta mix S, from which we then realize that delta mix H is equal to 0. There is no enthalpy of mixing. We also saw why this made sense intuitively. We saw that H is equal to U plus PV. It's an ideal gas, therefore U is equal to constant for ideal gas. And if it's an ideal gas, PV is equal to nRT and temperature is equal to constant. So we kind of saw this beforehand, but we derived it regressively. And another important thing we did was to plot these things last time. They looked something like this. So we are plotting versus X. So the one is over here. And we showed that, well, delta mix H is equal to 0. That's just a boring flat line. Delta G mix S. And I really think you should try to post your solutions to this as practice problems on the Slack channel to show that the curve actually looks like this, because this is quite important that it goes to 0 here and it goes to 0 with a slope of minus infinity on this side and plus infinity of this side. And once you have the delta G mix, the delta mix S is trivial because it's this one divided by a minus T. So it just goes on the top side. So this is again a common sense notion here that as soon as you mix a little bit of B, the entropy dominates. It wants to just get distributed. It's like throwing 2 needles in a haystack. When you throw 2 needles in a haystack, they won't probably stay together. You're most likely to put them random somewhere else. They will go wherever you want to go. It's not the best analogy because the needles don't move on their own. So a better analogy would be throwing, I don't know, 2 little insects at the same time in a haystack, right? They will just go randomly wherever you want. Wherever they want, not you want. So this is what we did last time. This was for mixing of 2 ideal gases. Now what we are going to do today is to talk about an ideal solution. So this was mixing of 2 ideal gases. We haven't really talked about ideal solution yet. Now, today we will start to talk about ideal solution, and this is the roadmap for this week. Is that we will talk about ideal solutions and regular solutions, and I will give you the gist of how things look like for them. So, for ideal solution, actually, the delta mix H is 0. Delta mix S is calculated using the expressions for an ideal gas, like we just did. For a regular solution, we will still keep this delta mix S as the ideal one, but this term over here will look like omega times XA times XB. And this omega is called the regular solution parameter. Atkins doesn't talk about omega at all, which I really do not like. I think it's a wonderful parameter. We will be spending time, I will be giving you my own notes onto what omega is. And omega really comes down to, let me write down the expression and we'll work through it in the coming classes. Omega is proportional to let's see if I have the constant right. So omega is proportional to the total number of atoms multiplied by Z, which is the coordination number of atoms. What does coordination number mean? Coordination number means if you have an atom, how many other atoms does it see in its neighborhood? So in this case, the coordination number for this atom is equal to 6. Z is equal to 6, right? Because it's 1, 2, 3, 4, 5, 6. Multiplied by energy of an AB bond, you're looking at a two-component system, minus energy of an AA bond plus energy of a BB bond divided by 2. So it's got a very molecular perspective. It really captures whether A likes to stick along with molecules of its type, other A's, or does A like to hang out with B's? And if it's an ideal gas, epsilon AB is 0, epsilon BB is 0, epsilon AA is 0, omega just goes to 0. Omega is equal to 0 for ideal gas. So what is this AB I'm talking about? So this is a roadmap. We are going to understand all of this in the coming few classes. This epsilon AB that I wrote over here corresponds to if you look at the distance between two atoms, let's say AB, this well depth is epsilon AB. How deep is the well? How much do A and B like to get together? So you can have such a well depth for AA, for AB and BB, and you compare all three, and that's how you get the regular solution model. And finally, you can write down here delta mix G, which will be minus T delta mix ideal S for an ideal solution. And for this one, it will be omega XA XB minus T delta mix ideal S. So this is what we are going to do in the next few classes. Of course, things don't stop here. Real solutions become even more complicated. Instead of thinking of the entropy as coming from ideal gases, you think of entropy also to be more general. And instead of just assuming this regular solution model for the enthalpy, this is better than the ideal solution, this term I wrote over here. We will do more complicated things. But for now, let's just talk about ideal solutions. If this regular solution thing confuses you right now, that's okay. Just take a mental note. We are going to come back to it and it will become completely clear. But let's first start with an ideal solution. So Atkins talks about regular solutions if you want to go and read. However, Atkins does not go really into what is omega. Maybe it does, but not in detail. So let's talk about ideal solution. What do we mean by ideal solution? So far we have looked at gases. Now we are talking about a container in this container, we have A and B existing in liquid form. So we have some liquid form and A and B. And on top of that, we have A and B existing in gaseous form. So we have the gas molecules for A and B. And we know this is in equilibrium. The gas A, so gas and liquid are now two phases, right? So here we have two phases, gas and liquid, and each phase on its own is coming from A and B. The gas has some A, the liquid has some A, the gas has some B, the liquid has some B. So we want to tackle this problem. We want to talk about what is the free energy of mixing for this ideal solution. And as you will see, the answer is basically what you did for ideal gases. Once again, we will get that the enthalpy of mixing is 0 and the entropy of mixing follows exactly the same equation. But the process of working through it is a bit complicated. Atkins even had a typo in this part, I think. I will tell you where the typo is. And let's work through it carefully. So in vapor or in gaseous form, in gas phase, I will use gas and vapor interchangeably. In gas phase, what can we say about the chemical potential of, and it's an, so A, B, both, sorry, what is my pencil doing? A, B are ideal gases. So what does that mean? In the gas phase, we can talk about, so mu of A, the chemical potential of A in the gas phase. How will that look like? That will look like some reference chemical potential, mu A naught in the gas phase, plus the pressure of A with respect to that reference potential. And we set that to be equal to 1, so I don't have to write anything in the denominator. We always talk about the reference pressure as 1 unit, whatever that unit is. Something in the chat. Is the top of the delta mix S also ln2? Yeah, it's no, this is not ln2, this is natural log. And should delta S for regular solution say real? I didn't understand your question, Noel. So you are asking about delta mix for the regular solution. That's going to be the same as the delta mix for the ideal solution. This is the same over here. Is the negative T for delta mix G for real solution? Or real is real, everything goes funky. All kinds of things happen. We are not going to get more real than regular. It'll give you a sense of how things look like, but real, all kinds of strange things can happen. So in the gas phase, we can write down that mu a G is equal to mu a naught G plus RT ln PA, where PA is equal to partial pressure of A and we also know that gas and liquid are in equilibrium. What does equilibrium mean to us at constant pressure and temperature? That means the chemical potential of A must be the same in the gas and in the liquid phase. Therefore, let's number this equation. This today numbering will be quite important. So let's call it as equation number 1. Mu A gas should be equal to mu A liquid. And you should be able to write a similar equation for B. We just do A, that's sufficient for our purposes. And we just wrote down that mu A gas is equal to mu A naught G plus RT ln P. Therefore, mu A liquid is equal to mu A naught gas plus RT ln PA. This is our equation number 3. using 1 and 2. Okay, great. Now, all of this, what we wrote till now, was for the mixture. Let's think about if it was not A and B mixed, but if it was pure things at the same time. Now let's consider if the liquid and vapor were pure A. Again, you could have done this for pure B also. The answer won't be any different. We just start with pure A. And let's use star or an asterisk to denote this scenario. And following Atkins convention here, I think it can be done in a better way, but it's a bit clumsy, but it's not too bad. So if this is true, then what can we say about mu A liquid? Now we are talking about mu A star liquid. If there was only A, we can still say that mu A star liquid is equal to mu A naught G. We don't need to put a star for the mu A naught because that's just the reference chemical potential for pure A, plus RT ln PA. But now we will have a star, which is showing what is the what would be the pressure be if things were if it was pure A. Okay, so this corresponds to pure A. In other words, all we are saying is that PA is equal to XA times PA star for ideal behavior, right? So if XA was equal to 1, you can see PA is equal to PA star. So this is partial pressure. And this is pressure of pure A. And once you start reducing the mole fraction, you introduce some other species, the partial pressure starts to go down, right? That's all we have done over here. What can we do from this? We can go back to our equation 2, go back to equation 2, and we can write down mu A liquid is equal to mu A naught G, but this mu A naught G that we had over here, we will use from this equation. We will use from this equation. And what does that look like? Then we get a mu A star L. So the operations I'm doing look a bit complicated. They look complicated to me the first time I read them, but it's not. It's just careful bookkeeping. Mu A star L minus RT ln PA star, right? Where did the minus come from? Because we took this mu A naught G and wrote it as a difference of mu A star L minus RT ln PA star and RT ln PA star. So, and we still have this term left over here. So it will be RT ln PA is equal to mu A star L plus RT ln PA by PA star. For ideal behavior, we know that is equal to XA. Therefore, mu A liquid is equal to mu A star liquid plus RT ln XA. This is chemical potential in an ideal solution. So this is an important equation. We haven't yet talked about delta mix in G for an ideal solution, but we are getting there. This is the key equation that will allow us to get there. So it looks very similar to what we did when we spoke about Gibbs energy, and we had an equation that looked like mu A L is equal to mu A star L plus RT ln P by P naught, right? It's the same idea over here. The partial pressure for an ideal gas is related to the mole fraction, and that's what we have used over here. So even if this derivation so far looks funky to you and it is a bit convoluted, like I said, this equation should make intuitive sense to you because we have seen something like this in the past. So,
Professor Torr,
yeah.
would you have to find it for B as well, or are you saying that?
Yeah, we'll have to do it for B also. Good.
And then would you add them together to get the total? Or
yeah, are you looking into my notes or something? That's exactly what we are going to do next. Good.
Thank you.
So let's do that. Good. So we just showed that mu A liquid, that's exactly what we are going to do. Mu A star plus RT ln XA. Similarly, mu B liquid is equal to mu B star, just like Zach said, plus RT ln XB. We did not derive this, but it's the same thing. Instead of B, you work with A and you get this equation, right? So this is how both of them change. And now we have to talk about delta mixing of why is my pencil doing this very strange thing? Delta mixing G. How do we do that? In order to do this, we have to think about, once again, G final minus G initial. What is G initial? G initial now is Na moles of A, but when you have pure A, we are using a star, right? So in this case, this is going to be Na mu A star L plus Nb mu B star L, and GF is going to be Na mu Al, because now it has changed due to the mole fraction. So if you put XA is equal to 1 here, pure A, what do you get? You get mu A liquid is equal to mu A star liquid, right? So it makes sense. Now you will have Na mu A liquid plus Nb mu B liquid. And now if you do the subtraction, delta mix G, that comes out to be GF minus GI. What is GF? GF is Na multiplied by mu A star liquid plus RT ln XA plus Nb multiplied by mu B star liquid plus RT ln XB minus Na mu A star liquid minus Nb mu B star liquid. So this term and this term cancels out, this term and this term cancels out, and we are left with Na RT. Oh, my pencil is being freaky. Na RT ln XA plus Nb RT ln XB. Therefore, delta mix G per mole is once again XA RT ln XA plus XB RT ln XB. We get exactly the same equation. That's wonderful, right? I think that's great. We got exactly the same thing. So if you forget all the derivation and everything, you can just go back to ideal gas and derive it. For ideal gas, it's quite simple. There was no business of stars and this and that. It was quite simple. That's what we get. Once again, delta mix S is equal to minus XA ln XA plus XP ln XP, and delta mix H is equal to 0. Even so, we showed this for mixture of two ideal gases. Now we have gas existing in equilibrium with liquid, and we get exactly the same thing. So what you're seeing right now is thermo getting funky in a slightly different way. Thermo is not getting funky due to complicated partial derivatives and things like that. It's getting funky due to accounting for what is the reference. Is it partial? Is it not? And for those of you who will do thermo in practice for your research projects, or when you go and work in some company, if you're doing drug discovery, for example, or you're doing battery material discovery, these things will matter enormously, this type of bookkeeping. And it also starts to get more complicated because you don't have ideal behavior. So instead of partial pressure, you have to deal with fugacity. And so applied thermo, so this part of thermo is also complicated, but mostly because ideal behavior does not hold true. But if you have these key concepts in place, it's not too hard. So we got our delta mix H, and this allows us to talk about something else, which you have probably seen in your chemistry earlier. Pakora, he's expecting belly rubs from me right now. Go away, I'm teaching, go away. So what did we do here? In order to get here, we wrote that PA is equal to XA times PA star, right? The partial pressure is equal to mole fraction multiplied by the partial pressure, multiplied by the pressure of the pure species. So we can draw it in a plot. We can draw it in a plot that looks like this. We have pressure, and on the right, on the x-axis, we have XB, which goes from 0 to 1. And for an ideal gas, let's think about the net pressure of the system. So net pressure is always going to be PA plus PB, right? When XB is equal to 0, then PB, so here we are talking about ideal behavior. So when XB is equal to 0, what is going to be the value of PB? Any ideas? For ideal behavior. Zero. How about for non-ideal behavior? When XB is 0, what would PB be then? What would be the partial pressure of B in a solution when there is no B? Precisely, there is no B. So at the end limit, it's always going to be 0. PB is equal to 0. This little thing is true for both. So, so PB is equal to 0 and PA is equal to PA star. This is assuming we have ideal behavior. So we start over here. P is equal to PA star. And similarly, you can see when XB is equal to 1. So this is true in general, the limiting value. Similarly, when XB, before anyone protests later, what did I scribble here? Let me write it down clearly. In general, when XP is equal to 1, then so P is equal to PA is equal to PA star. When XB is equal to 1, P is equal to PB is equal to PB star. Again, in general. And let's say PB star is higher than PA star. It could have been lower. I don't know. I just put it higher, okay? The in the middle though, so at the ends, at the left end, it's going to start at PA star. At the right end, it's going to PB star. It differs from ideal in the middle for a real solution. Okay, so for the question is, how does it look in the middle for an ideal solution? Let's first do that. So we got our endpoints. Now, if I wanted you to think about how should it look like in the middle for an ideal solution, how will it look like? It's just going to be linear, right? For an ideal solution, this curve will be exactly linear because we are talking about P is equal to 1 minus XB multiplied by PA star plus XB multiplied by PB star. This is the equation of a straight line, right? PA star and PB star are just two numbers and it is linear in XP. So it looks like this. This is the sign of ideal behavior, and chemicals which follow this property are known to follow, are said, what's happening with my English? It's screwing up like my Apple Pencil. if a given solution follows this behavior, it is said to follow Raoult's law. Raoult's law says that the pressure of a system increases, the pressure of a solution increases linearly between the two endpoints, A to B. Raoult's law is linear change in pressure of a solution. And as you can see, ideal solutions will follow Raoult's law. So it's almost synonymous, it's not almost, it is synonymous. An ideal solution will follow Raoult's law. In reality, that is not the case. You can have deviation from Raoult's law, and the deviations can look as follows. A positive deviation can look like this. A negative deviation can look like this. You might ask, does it always have to be positive or negative? Actually, I don't know. It might very well cross for, and I missed a L in my Raoult's law. So this one is called positive deviation. This one is called negative deviation. And when we do our regular solution model, this will boil down to that term omega. When omega is equal to 0 in the regular solution model, we get the term in the middle. We haven't done that yet, but that's what we'll be doing next. When omega is equal to 0, the delta mix H is equal to 0, and we recover linear behavior of the pressure as you go from one end to the other end. In fact, let's draw this curve again here, the same thing, and let's look at it in a bit more detail. So we are talking about XB going from 0 to 1, and we are talking about the net pressure of the system, P of the solution, okay, combined with A and V. So what did we just say? We said that at this end, it's always going to be PA star. It's this end, it's always going to be PV star. That's constrained. If you have an ideal solution, it's going to be linear. This is ideal solution. This is called Raoult's law. There are typically, what was the term on the regular solution graph? It was omega. I will just write it down over here. And we are going to talk about regular solution plenty. In practice, you can have a positive deviation from Raoult's law, or you can have a negative deviation from Raoult's law. And we will see that is this true, what I'm writing? Let's be careful. Yeah, this will correspond to the term omega in regular solution being positive. This will correspond to the term omega in regular solution being negative. And we will, if we haven't really talked about omega yet, but even without doing it, you can get a sense of why omega is what it is. I would like you to think about the enthalpy of AB relative to the enthalpy of AA plus BB on an average. So if these two enthalpies are same, then we get ideal behavior. Right? Because per construction, delta mix H is going to be 0. If HAB is more than HAA plus HBB by 2, it means that when you mix it together, there is an enthalpy cost. In this case, delta mix H is going to be positive. And if HAB is less than HAA plus HBB by 2, then delta mix H is negative. Why does this mean that the pressure, so it's fine, okay, we say that delta mix H is positive. Why does this mean that the pressure is higher than the ideal behavior? That's the thing you need to think about physically. if A does not like B due to enthalpy reasons, there is an entropy reason. Entropy reason is already accounted for in our straight line, right? This accounts for entropy, assuming it to be ideal. The entropy is already accounted for in the straight line. The things that we have not accounted for are the enthalpy. If delta mix H is positive, why should the partial pressure, why should the pressure of this solution be higher than that of the ideal behavior? Any ideas? Does it make sense? Does it not make sense? Any comments? It's A doesn't like B, right? So it wants to escape through the container. You have mixed it together. It's like, I don't like you, I want to escape. So you feel a higher pressure. However, if A likes B, which is if HAB is less than HAA and HBB separately, it's like, oh, I like to hang out with you. It doesn't try to escape out of the container. So you can see why this enthalpy cost over here leads to positive deviation in pressure, and why enthalpy gain says, okay, I'm fine. I will, the pressure actually goes down. Okay, good. So we haven't yet done regular solution, but we are starting to see hints of it. An ideal solution would have again given delta mix H is equal to 0 and delta mix S, the same term as we derived last time for ideal gases, and the behavior for the pressure would have looked like a nice linear plot that goes from PS star to PV star, and that is what you have most likely seen in chemistry earlier, known as Raoult's law. So, okay, any questions about anything? Okay, someone posted on the Slack channel, is the key meant to be posted for the, I tried opening it, but Google is saying I need to request access. I will change that. Sometime in my Google Drive, there is some problem. I will change that after the class. Sorry about that. Okay, good. So notice something. Ideal solution. And it's a good point to summarize what we have done so far for an ideal solution. For an ideal solution, delta mix H, and we will call it as ideal, superscript, is equal to 0, and delta mix ideal S is not equal to 0. And more than just not equal to 0, we actually derived what it is. We saw it is x ln x plus 1 minus x ln 1 minus x term. So these are ideal behaviors. Almost nothing in life is ideal. The closest you can get to ideal behavior is by looking at rare gases talking to each other, like argon or neon or krypton, because they are as close to the ideal potential energy curve that you can think of. But even there, you have a finite radius. Even there, you start doing van der Waals is a better model for this. So almost always this will break down. But ideal behavior is a nice model to aim for that allows thermodynamics to be tractable. It allows thermodynamics to be something we can write down in nice, simple equations and think about it. You can already see a straight line is better than some arbitrary curve, right? We know how to deal with it. We don't know what's the equation for this curve, the blue and the red curve that I drew over here. So given this, the way we proceed from here is to talk about something known as the excess function. The excess function captures how different is something from ideal behavior. What does it mean? we could have any state function. So it's got to be for a state function. Otherwise, it just doesn't make sense to talk about it. If it depends on path, then what are we even talking about? And it is denoted as a XE. This is delta mix. What is the change in that state function if you mix it in reality, not assuming an ideal behavior, minus what is the change in that function if you calculated it assuming ideal behavior? Okay, so for an ideal solution, we just saw that S and excess entropy, for example. Let's think through this just to make sure that we are on the same page. I want you all to think about the excess entropy for an ideal solution. I want you to think about excess enthalpy for an ideal solution. And I want you to think about the excess volume for an ideal solution. Let's start with excess enthalpy. What is it for an ideal solution? This is 0. Why is it 0? Because both terms are 0, right? For an ideal solution, everything is 0. So for an ideal solution, excess enthalpy is also 0 because we are just calculating delta mix S ideal minus delta mix S ideal. It's going to be 0, right? Everything is 0 per construction. There is no magic over here. The excess enthalpy, the excess entropy, the excess volume, any state function that you can think of is going to be 0 for an ideal solution. In general, it's going to be higher than 0 or lower than 0. It will be some non-zero value. Okay, so this will be our, it's not really our framework, but this is a term that you will encounter. Atkins talks about it and you will encounter it every once in a while. So now we are ready to start talking about regular solutions. Regular solutions, just to use this terminology over here, we will say that excess entropy is equal to 0. Okay, what does this mean? Therefore, we are going to deal with the entropy of mixing in a regular solution. We will set it to be the same as the entropy of mixing in an ideal solution. We won't care. We will just use the same expression that we derived last time. What is that expression? We just wrote it down. That is minus RT XA ln XA plus XP ln XP. We are not going to challenge this entropy expression. This term, however, will be allowed to be non-zero. That's our regular solution model. And we will derive an expression for this. Now, before we go into doing all that, this is where we will start next time. Today, I'm going to stop. Regular solution gets quite, it's a really fun derivation. It's going to be a bit mathematical. Okay, so get ready. It's going to involve counting number of neighbors. It will, it's if you like counting things, it'll be fun. It's a bit of counting. But I want you to think about, for today, when do you expect this to break down? Do you expect that at times this will be a bad model? What are the other forms of entropy that we are mixing over here? Oh yeah, good point. I got an extra T over there. You're right. You're paying attention. That's great. So this is minus R because we derived T. So when will this break down? It will break down when ideal behavior breaks down, right? So that's per construction. When the gases are no longer behaving as ideal, it will break down. In fact, it will also break down. And so let's not say also. Another way of thinking about it is what are the different ways in which ideal behavior can break down. So it will break down, for example, if quantum mechanics starts to dominate, you have to think about entropy coming due to the electron. It will start to break down if particles have finite size. It will almost always break down. However, it is still quite useful. The simple model for entropy that we derived using XA ln XA plus XB ln XB is still quite useful. For real solutions, which we are really not going to do until we talk a little bit about chemical equilibrium, this enthalpy of mix, excess enthalpy will be non-zero, and excess entropy will also be non-zero. And that is what you almost is most useful to describe anything real. But this simple formula for entropy that we derived using ideal behavior is actually quite powerful. As you increase the temperature and decrease the density, it starts to become more and more accurate, right? Because that's when things start to behave more and more ideally. So next time we are going to think about this excess enthalpy. In fact, we will show that the delta mix H is given by omega XA XB, where omega can be directly calculated from looking at the well depth of an interaction. Why is this very useful? Because you can calculate this well depth by doing quantum mechanics on your system or by doing spectroscopy. You have a way to get this well depth. This epsilon AB and epsilon AA and epsilon BB is something you can directly calculate for the pure A and the pure B by doing some sort of quantum mechanics or spectroscopy, and then you are ready to talk about regular solutions. So in fact, there is a whole industry where people try to calculate more and more accurate terms for this delta mix H to make it useful. Okay, so this is a good point to stop today. Next time we will talk about regular solutions, and we will work through the math carefully, and then we will continue our study of phase diagram. So I will be having office hours today, 11 to 11:45. I'll stop a bit early because typically people run out of things to ask. 11 to 11:45, I will be there. Some things are still pinned on the Slack channel. I haven't forgotten them. You can remind me. I will be addressing everything. Latest by the end of Thanksgiving break, I will address everything. And in this homework, please make note of things that are confusing to you so that right before the final exam, I hope to do at least 2 full classes of complete review of the whole semester, 2 or even 3. At some point, I will stop, and instead of just giving you new concepts, I will stop and take a full week of going systematically from beginning till end and giving special attention to the topics I hear from you are confusing to you. Because we have done a lot of things. You have all done wonderful so far. So, and we will do reviews. So I need to know what is it that is not clear to you. We have one homework after this. So this is homework 6, then there is homework 7. I could have done a homework 8, but I don't think I will do that. It will be too much work. Some of the homework type problems will be in the final exam. So final exam will have slightly more components from the later work, which doesn't mean you have to forget about first law of thermodynamics and kinetic theory and things like that, but it will have slightly more components. So this homework number 6 is due the day after tomorrow, and then after Thanksgiving, right after Thanksgiving, there will be homework number 7. It's posted on the Slack channel. If you go and see, it's pinned. Okay, so see some of you in office hours.